Okay, let's get right into it. What if I told you there's a kind of mathematical cheat code for the universe, a hidden rhythm that helps solve some of the world's most difficult problems, and it's been hiding in plain sight this whole time? Today, we're going to unpack a discovery that could seriously change how we see everything from factory logistics to how science itself actually works.
So, it all kicks off with this really strange puzzle. Our best computer science theories, the most powerful models we have, they all predict that certain problems should be, well, almost impossible to solve. We're talking about problems with a staggering number of possibilities. But in the real world, we solve them all the time, and way faster than we should be able to. So what's going on?
Just look at this. Theory says that perfectly laying out a computer chip, or finding the absolute best layout for a new hospital to save nurses' time, it should be a total computational nightmare. Yet, we design unbelievably complex chips that work, and we find really smart, efficient ways to organize hospitals and plan factory schedules. There's a huge gap here, this real-world advantage that our textbooks just can't explain.
And the answer, it turns out, isn't that we're just getting lucky. No, the research we're diving into today points to something way more profound. It seems that real-world problems, because they actually have to exist in the physical universe, have a hidden structure, a secret order. They seem to march to the beat of a very, very specific mathematical drum.
To get our heads around this, we need to borrow a quick idea from physics called quantization. It sounds complicated, but it's not. Just picture a ramp versus a flight of stairs. A ramp is smooth, continuous. You can stand anywhere on it. Stairs are different, right? You can only stand on a few specific, discrete steps. Quantization is just the idea that a lot of things in our universe work like those stairs, not the ramp. They come in distinct, separate packets.
And here is the absolute mind-bender. The good solutions to these tough, real-world problems, they aren't just scattered randomly all over the place. They are quantized. They clump together at very specific, predictable levels, almost like books sitting on shelves. And get this, all of those shelves, all those levels, are multiples of a single fundamental number.
So what is this magic number? It's 1/7. That's it. This simple fraction, 1 divided by 7, seems to be the hidden rhythm we've been looking for. The best answers to these super complex problems consistently cluster around values that are multiples of this one constant.
Now, I know what you might be thinking. 1/7? What's so special about that? Well, it's not just some random fraction. It's mathematically unique. As a decimal, it creates this beautiful, infinitely repeating sequence. 1, 4, 2, 8, 5, 7. Over and over forever. This special property suggests it's not just some coincidence, but a fundamental constant with real meaning.
Of course, that is the million-dollar question. An interesting pattern is one thing, but proof is something else entirely. How can we be sure this is a genuine property of reality and not just us seeing faces in the clouds? And this right here is the smoking gun. Researchers put this to the test. They measured something called quantization error, which is basically how well the answers fit this 1/7 pattern. For real-world problems, the error was tiny, just about 7%. But for purely abstract, made-up math problems, the error was a whopping 79%. That is an 11-fold difference. They ran over 400 trials, and there was zero overlap, not once. So the conclusion is just inescapable. Real-world problems behave in a completely different way than their abstract cousins. They're not just a subset of general math problems. They seem to be a distinct class of mathematical object, one that has the rules of physics baked right into it. Okay, so we've found a cheat code for reality. What's the next logical step? Well, you build tools to exploit it, of course. This discovery isn't just some cool academic idea. It points us toward a new and much, much smarter way of solving problems.
This leads to a whole new approach, an algorithm called harmonic search. Instead of just blindly guessing and checking, which is like searching for a needle in a haystack in the dark, this algorithm works with the structure of reality. First, it looks for that hidden 1/7 rhythm. Then, it identifies those energy shelves where all the good solutions are hiding. And then, it can just intelligently jump from shelf to shelf, completely ignoring the massive empty spaces in between to find the best answer incredibly fast.
And the real-world advantages here are immediate, and they are huge. We're talking about getting faster, better answers for critical industries. For a company managing a global supply chain, this means smarter logistics. For a hospital, it's better staff schedules. For a tech company, it's a faster way to design the next chip. By creating algorithms that are literally tuned to reality, we get solutions faster while using way less computing power. That saves an enormous amount of time and money.
But the implications here are so much bigger than just faster algorithms. This discovery challenges the very way we've been approaching science and knowledge for a long time. It's a true paradigm shift.
This quote really just nails it. For centuries, we had to trust that a scientist from a famous university was telling the truth because there was no easy way to check their work. But the code behind this discovery? You can run it on a laptop. You can verify the results in minutes. Trust is shifting away from the person and toward the proof itself.
And you can see the change right here. The old way was all about institutional gatekeepers and trusting fancy credentials. The new way is about democratized research and trusting code that anyone can verify. This gives a huge outsider advantage to people who aren't weighed down by old theories and can just engage directly with the raw data of the problem.
Ultimately, what this suggests is that for decades, an entire field of smart people might have been looking at optimization completely backwards. It's just a powerful reminder that sometimes the biggest breakthroughs don't come from more complexity, but from someone stepping back and asking a really simple, basic question nobody else bothered to ask. And so that's the final thought I want to leave you with. If our abstract models were this disconnected from the real, physical problems they were supposed to describe, what other massive blind spots do we have? What other hidden rhythms of reality are just out there, waiting for someone to listen closely enough to the world to finally hear the music?